Welcome, everyone. For today's prep, we're going to start to look at trigonometric integrals. And the case we're going to be considering is the case where we have odd powers of sine and cosine. All right, so first, before we even get to the strategy, I just want to make a little notational remark here when we're talking about powers of sine and cosine and other trig functions as well. So in the first example that we're going to do, we have cosine of x cubed. When we write, a lot of times when we write powers of sine and cosine and other trig functions, we put the exponent, looks like we're putting it on the name of the function. What we really mean though, and this is just to kind of help cut down on the amount of parentheses, what we really mean is cosine of x, that whole thing is getting cubed. All right, so just a little note there about our notation. All right, so when we have a trig identity like this, where it's sine squared plus cosine squared is equal to 1, really what we mean is we're doing sine of theta, and then we're squaring that whole thing. And cosine of theta, and we're squaring that whole thing. But just so we don't have to write so many parentheses, a lot of times we put the exponent just on the name of the function. All right, so we're going to be considering the case where we have odd powers of sine or cosine. So at least one of them has to be an odd power. So maybe sometimes both. So to see this strategy, we'll look at an example. We'll go through the strategy and then we'll come back and read over this. So let's look at example 1. We have cosine of x cubed, and we want to integrate this. So our strategy is to first identify which trig function has the odd power. So in this case, it's cosine. No surprise there. And the idea is we're going to take one of those cosines. So we've got 3 of them to work with here. We're going to take one of them. We're going to peel it off, and we're going to put it next to our differential. So we had 3 copies. Now we're peeling off the top one. So I have 2 copies here, and next door I have 1 copy that I'm multiplying. All right. So this cosine x that we move next to our differential, we're going to save this. We're going to put this aside. And what we're saving it for is ultimately we're going to do a u substitution to help us finish this integral. So this cosine x dx, that's going to get involved with our differential. All right, so once we've peeled that off, everything here, everything that's left over, we want it in terms of the opposite trig function. So in this case, we're going to change all of our cosines that we have here. We want to get it all to the opposite trig function. So you want to think of sine and cosine as kind of like opposite functions in terms of this trig identity. So right now, we have cosine squared. We want to change that to sine. So we want to change all of those to sine. And we have that trig identity that helps us with this. So we know that cosine squared, well, we know that sine squared x plus cosine squared x is equal to 1. So here we have cosine squared. So we're just going to solve this equation for cosine squared. And we're going to move the sine squared over to the other side. And that'll allow us to say 1 minus sine squared times cosine x is now our integral that we're trying to solve. So all we did is we changed this cosine squared term using that trig identity to 1 minus sine squared. And again, we're saving this cosine. That's going to be our differential. That's going to become part of our differential when we do this u substitution. So the goal is put this aside. Everything you have left over has to get changed over to sine in this case, which we did. So now we're ready for our u sub. And we're going to let u equal the opposite trig function. So we got everything in terms of sine. So we're going to let u equal sine here. And then we kind of go through like a regular u sub. So derivative of sine is cosine. We multiply by our differential. And now we see how everything's going to fit together. So we see that the cosine x dx that we were saving, well, that's just going to become our new differential. And then our u is sine x. So now this is just a regular u sub. So we're going to fill that in there. And we're going to fill the differential in. So this ends up being the integral of 1 minus u squared times du. Get the antiderivative. So the antiderivative of 1 is u. Antiderivative of u squared is 1/3 u cubed. And then we're doing an indefinite integral, so we throw on our plus c at the end. And then finally, we just got to get back to x. So we're going to fill back in with our sine. So we get sine x minus 1/3 sine of x cubed with our plus c at the end. Okay, so that's the idea. Let's try another example. But before we do, let's go to back to our strategy here. So when we have odd powers of sine and cosine, we want to first identify the trig term that has the odd power, and we're just going to factor off one of those trig terms from that odd power, and we put it next to our dx. Then everything that's left over in the integral, except for that one that we peeled off, we want to get to the opposite trig function. So again, for the purposes of this, we want to think of sine and cosine kind of as opposite functions. We're always going back and forth between the two of them. So if we peel off a dx, then we want to get everything, or if we peel off a cosine, we want everything back in terms of sine. Then from there, we do a u substitution where we set u equal to the opposite trig function. And then we just go through the substitution rule. So let's try one more. So let's look at example 2 here. And the function we're integrating is sine times cosine. And even though they're not written, both of these have an exponent of 1. So both of them have an odd power here. So there's kind of two ways we could do this one. For the practice, probably the best way is, well, cosine x is already there. So let's just peel off that one copy, put it next to our differential, and then everything left over has to be sine. So we're going to save this one cosine, and then everything else has to be sine. Which, in this case, it already is. So we're good. So then from here, we're going to figure out our u substitution. So because we peeled off that one cosine term, we're going to let u equal the opposite trig function. So we're saving this cosine, so that means we're going to let u equal sine. So then the differential, we calculate the derivative, we get cosine x multiplied by dx, and now this just becomes just a regular u sub. So we can fill this in and then fill in our differential. And so we end up with the integral of u du, which is 1/2 u squared plus c, and then we convert back to x. So we get 1/2 sine squared plus c. Now you could have done this one the other way. So I could have said, well, my sine x is odd, so I could have rearranged the terms and moved that next to the differential. So as practice, let's just kind of see how that would look. So let's suppose that we rearrange this, and I move the sine x next to my differential. All right, so now I'm going to save that one for later. We're saving that for our u substitution. So that means because I'm saving sine everything that's left, except for that one sign, everything left has to be the opposite trig function, which in this case, it is. So everything that would be left over, we would want as cosine x. So sometimes there's a little bit of work there to do. In this case, it's kind of easy. All right. So now we would do a u substitution. So our u substitution in this case, since we peeled off that sine x and we put it next to our differential, we're going to let u equal the opposite trig function. So we're going to let u equal cosine. So then the derivative of cosine is negative sine, multiply by dx. And now you can kind of see here, you got to do a little bit of work with the differential. You know, what we're used to with substitution rules. Sometimes the differential is not always a perfect match. So in this case, we have the sine x dx, but then we have this extra constant multiple in front, this -1. So our strategy for handling that is just to solve for the matching terms. So when we do that, we get sine x dx is equal to -1 du. So we're just dividing by -1 here. And division by -1 is the same thing as multiplication by -1. All right, so once we have all this, now it's just, again, a regular u substitution. So we're going to fill in our pieces. So we'll switch over our differential. We'll switch over our function. And when we fill in the pieces, we're going to end up with the integral of u times -1 du. And we get the antiderivative. The -1 is a constant multiple. Let's throw that in front. And then the antiderivative of the u is 1/2 u squared plus c. And then finally, we convert back to x. And we end up with -1/2 cosine squared x plus c. So you don't have to do it both ways. You only have to do it one way. So pick the way, for something like this, pick the way that you like. But it's just to show you, depending on how you do these, sometimes there's more than one correct way to do these trig integrals. And depending on how you do it, your answer might look different than someone else's answer. So in this case, the antiderivative we got here is 1/2 sine squared plus c. Our antiderivative down here is -1/2 cosine squared plus c. Now these might look like different functions, but as we've seen, there's a trig identity that kind of relates sine squared and cosine squared. So even though these answers might look different, they're equivalent. So just because, if you're practicing along in class and I do it one way and you do it another way, just because we get answers that look different doesn't necessarily mean that it's incorrect. All right, so we'll try example 3 in class. So we'll see you then. Bye-bye.